Salinomycin, the hidden weapon against cancer's most dangerous cells. Once upon a time, in the world of medicine, a humble antibiotic named salinomycin was used primarily for treating infections in animals. It lived a quiet life as a veterinary drug, helping to keep livestock healthy and strong. But little did anyone know, salinomycin possessed an extraordinary secret. It had the power to fight one of the deadliest enemies in the human body: cancer stem cells, CSCs. CSCs, the villains of the cancer world, were unlike ordinary cancer cells. They could regenerate, resist treatment, and even hide from chemotherapy's powerful blows. They were the masterminds behind cancer's cruelest trick: recurrence. Just when everyone thought the battle was won, these sneaky cells would rise from the ashes and reignite the disease. But salinomycin, with its unexpected abilities, had the potential to change the course of this battle. One day, scientists stumbled upon salinomycin's hidden strength. In 2009, Dr. Piyush Gupta and his team at MIT made a discovery that would forever change how we view this unassuming antibiotic. They found that salinomycin could reduce the population of CSCs in breast cancer by more than 100-fold, a result far superior to what standard chemotherapy could achieve. Suddenly, salinomycin was no longer just an animal drug. It had a new mission: to help humanity in the fight against cancer, a warrior through ferroptosis. Salinomycin's power came from a process called ferroptosis, a form of iron-dependent cell death. Imagine iron as a double-edged sword inside cells. While essential for life, in high amounts, iron could react with oxygen and produce toxic molecules known as reactive oxygen species, or OS. These molecules wreak havoc inside cells, causing damage so severe that the cell would eventually die. Normally, cancer cells, especially CSCs, were experts at keeping ROS under control, using antioxidant shields to defend themselves. But salinomycin knew exactly how to break through. When salinomycin entered the cancer cells, it caused iron to accumulate in tiny compartments called lysosomes, which act like the cell's recycling center. Overloaded with iron, these lysosomes began to leak, allowing ROS to flood the cell. Unable to stop the onslaught, the cancer stem cells succumbed to this overwhelming damage. Through this process, salinomycin targeted the very heart of cancer's defenses, rendering CSCs powerless. The do-ent pathway showdown. But that wasn't all. Salinomycin also knew how to shut down the do-ent signaling pathway, one of cancer's most powerful weapons. In many cancers, including colorectal, breast, and even certain leukemias, the do-ent pathway was like a secret communication line that allowed CSCs to stay strong, proliferate, and avoid destruction. By disrupting this pathway, salinomycin cut off CSCs' ability to regenerate, leaving them vulnerable to attack. For years, scientists had been searching for ways to block the do-ent pathway, knowing that it could be the key to defeating CSCs. Salinomycin, with its unique dual attack, both through ferroptosis and do-ent pathway inhibition, proved to be one of the most potent solutions. It was like a warrior wielding two weapons, striking at cancer cells from multiple angles. A dilemma of power and poison. But as with many great warriors, salinomycin's strength came with a price. It wasn't just lethal to CSCs, it was also toxic to healthy cells. The same abilities that made it such an effective cancer fighter also posed significant risks to patients. In animals, high doses of salinomycin caused serious side effects, including damage to the nervous system. The toxicity dilemma made researchers pause. Could salinomycin ever be safely used in humans, or would its power remain untapped due to its dangerous side effects? Scientists around the world began working on solutions. Some sought to modify salinomycin, creating derivatives that would retain its anti-cancer properties while reducing its harmful effects. Others turned to innovative delivery methods like nanoparticles, hoping to encapsulate salinomycin and direct it specifically to tumors, sparing healthy cells in the process. These efforts were like crafting a specialized suit of armor for salinomycin, one that would protect the patient while allowing the drug to strike at cancer's core. The hope of combination therapies. Salinomycin's story doesn't end with its individual power. Researchers also saw its potential as part of a larger team in combination therapies. Paired with chemotherapy or other treatments that weaken CSC defenses, salinomycin's effectiveness could be amplified. By hitting cancer cells from multiple fronts, through ferroptosis, do-ent inhibition, and additional therapies, Doctors hoped to eliminate not only the bulk of the tumour, but also the CSCs lurking within. Some even dreamed of combining salinomycin with other ferroptosis-inducing agents, like artemisinin and sulfasalazine, to create a formidable alliance against CSCs. Together, these drugs could overwhelm the cancer cell's defences, ensuring that none escaped to cause a relapse. The possibilities were exciting, and researchers eagerly awaited the day when these combinations would be tested in clinical trials. A glimpse of the future. While salinomycin's toxicity remains a challenge, its journey as a cancer-fighting agent is far from over. Scientists continue to work on finding ways to harness its power safely, and its dual action against CSCs, both through ferroptosis and WNT inhibition, makes it a unique and valuable tool in the fight against cancer. The story of salinomycin is a testament to the potential hidden in even the most unexpected places. Who would have thought that a drug used for farm animals could one day hold the key to defeating one of the deadliest foes in cancer biology? And while the challenges are significant, the promise of salinomycin keeps researchers moving forward, driven by the hope that one day this remarkable drug will play a starring role in the battle against cancer.